Okay, so guys, what I would like to do is talk with you about every question on the assignment except for question 13. We'll talk about 13 maybe momentarily, but guys, what questions, and remember the goal here, right? By midnight tonight, you need to be able to say it is done completely and you got all your questions answered. So guys, with that said, what do we need to talk about so that you can fairly say you've got all your questions answered? Except for question 13. Please, go ahead. I'm at a huge disadvantage. I don't have the assignment. Tell me what it is. Oh, yeah, good question. We're maybe splitting hairs here, and here's why. You understand that if something is heterogeneous, if you grab here and if you grab here, you're grabbing different things. It's not the same thing the whole way through. Now, if you grab over here into a cup of ice water, you might get liquid water. And if you grab over here, you might get solid ice. So in that sense, it is heterogeneous because there are phases. There's the liquid phase and the solid phase, and there are interfaces where the liquid touches the solid. With that said, why do you have a problem with that? Because it's all water, right? Yeah. So if you were thinking of it that way, then you could argue that that would in fact be a compound because it's water, whether solid or liquid, it's water the whole way through. That's why we put it on the assignment, because it makes you sort of think through that. So if you put compound as your answer, you're actually okay. Okay? What's that? Okay, but what about this? Was your previous answer compound or was it like solution or element? Okay, and understand that would not be the case because the ice is not dissolved in the water. Is that okay? Okay. Guys, what else? What else would you like to talk about? Are you all okay? I'm more than fine for you guys to be okay. I don't mean to squeeze water from a rock. You guys are really okay? Yeah. Number 9. Number 9. Oh, yeah. Okay. So physical properties of substances are things that we can observe about a substance without creating something new. But we can also use some of these to separate things. Like, for example, probably the easiest to talk about is density. Because when we did that lab last time and we spun the things in the centrifuge, why did the solids go to the bottom and why did the liquids end up on top? And the answer is because of their density. When you spin something, the more dense stuff goes to the bottom, the less dense comes to the top. You can also separate things by stuff like boiling point. And that's how we got the water away from the salt in the salt and sand lab. We heated it up, the water boiled off. It wasn't hot enough to boil the salt, so the salt stayed behind. So those are examples of ways that we can separate things. Is that okay? Another example was solubility. Sand does not dissolve in water, but salt does. So when we added the water to the salt-sand mixture, the sand did not dissolve. It's not soluble, and therefore we could separate those as well. Is that okay? Yeah, that salt and sand lab actually has a lot of good stuff going on inside of it. Guys, what else? Okay, so what about question 13 on the back? Guys, there's no way for us to grade that. We can't. There's 11,000 different answers. So if you completed it, that's fine. If you didn't, you need to in preparation for saying that it's done by midnight tonight. But guys, with that said, do you have any questions about your answers and whether or not they were correct or you're all okay? Please. Iron what? Yeah. So if you're taking iron supplements, the iron in those supplements is definitely an element. Here's something really interesting, though. I've done this before, which is weird. They also put iron in cereal. Like if you read a cereal box, it says fortified with iron. If you take a box of cereal, put it in a blender, add water and turn it on and turn it into mush, and then if you stick a magnet in it, you'll actually get little chunks of iron that stick to the magnet. They're literally little iron filings that are hidden in the cereal flakes, and you can actually pull them out with a magnet. It's really weird. Yeah, Google it. Look it up on YouTube. There's videos of it. So, guys, what else? You all okay? Yeah. Water is definitely a compound. It's hydrogen and oxygen bonded together. Yeah. Anything else, you guys? You guys are geniuses. Okay. So, let's do this. Make a mental or physical note to yourself to record this assignment before midnight tonight. Put that away. And then, guys, let's just do this. You need to get your periodic tables out of your binders. And I printed all of your class notes for you. Yes, I know. I'm that kind of guy. And then, guys, I'm going to give you your homework right now because we're going to transition into it at the end of the day. But we are going to talk about what's going on before we get started. Are you a Doctor Who fan? I love it. There's been like, what, 15 Doctor Whos or something like that? It's a ton, right? Is it really 13? Oh my gosh. So guys, these are your class notes that I just gave you. Here comes your homework. Hey guys, while I'm distributing these, please remember that remediation is also today. It's today after school, 12:45. Come join us. If you are qualified and ready to go, just don't forget about it. Today is going to be a busy day for everybody. Okay, there's your homework. All right, so guys, forgive me for dropping a bomb in your lap a couple seconds ago. I assumed that you guys knew about what's going on, and apparently you don't. So we need to talk. So guys, first things first. Right now, probably the only thing worse than the struggles that we're fighting against relative to this disease is all of the rumors and misunderstandings and political and social agendas that are getting all tied up in this, which are not hurting us physically, but they're hurting us emotionally, socially. So guys, I'm going to ask you this first. Please, as best you can, talk about this positively. Guys, understand that it's really easy to stand back and throw stones. It's really easy to stand back and go, how dare you? And guys, understand, I'm hot in the middle of that. My daughter has been doing everything right. And we got the email yesterday that she's been quarantined, actually 2 days ago, she's been quarantined at Timpanogos, and it's just simply because she went to class one day. She has to miss her next 4 volleyball games. Guys, we are hot in the middle of this as well. But understand that when I look at this, I know that the people that are making these decisions are doing the very, very best they can in a really difficult situation. With that said, we're not going to share numbers. If you hear people talking about numbers, you need to immediately distrust those people because they're wrong. Guys, these numbers are not public. I don't know them, and I'm on our leadership team. About this is how many cases are at Orem. They're lying. They don't know. If they start talking about how many people are quarantined at Orem, they're lying. They don't know. So guys, we are going to talk kindly and productively about this to each other. okay? You can go home and freak out and punch walls and do whatever you want. But guys, when we talk about this, we're going to talk about this well. So here's the deal. You guys understand now that Orem and Provo have both been switched to orange, right? We were yellow, we've been ramped back to orange. Guys, right now, 42% of all of the COVID cases in the state are in Utah County, and we only account for 20% of the population. Guys, we are the reason that Utah is blowing up. And guys, right now, those explosions are happening in the 15 to 24 demographic. Understand a lot of those are at BYU and UVU, but they're also here. The problem is that we're now seeing a lingering increase in the number of older and younger people that are also getting sick. Our hospitalization rates are going up. Our positivity rates are going up. It used to be that about 5 to 8% of the people that get tested are positive. In Utah, right now, it's 13%. A lot of people are getting sick right now. Understand, we're not in danger, but we do need to address this. So, with that said, we've also seen a spike here at Orem High School. Our numbers are going up. You are not in danger. But guys, we are seeing our numbers rise, and so last night the school board, under the counsel of the Utah County Health Department, decided that we need to throttle back a little bit and give ourselves some space. So guys, we are going, to a blended model on Monday. So today and tomorrow are normal class periods. You do not have school on Friday. On Friday, your teachers are going to get together and they are going to figure out how they are going to handle this. And then when we get back next week, it will be an A day, B day, and that will be letters A through K. If you're L through Z, you stay home. Wednesday, Thursday, A day, B day will be L through Z, A through K stays home, and then we rinse and repeat. So Friday, Monday will be A day, B day, A through K, and so on. We will do this for 2 weeks, and then we will reevaluate. Pleasant Grove did this a couple weeks ago. At the end of 2 weeks, they're already back in school. So guys, we can fully expect that this is only going to be 2 weeks. It's just to sort of fan out a little bit to give us some more space to slow down the spread. So, guys, with that said, we need to talk. You are going to be getting emails from a lot of people. You're going to be getting emails from the school district, potentially county health, and you'll be getting emails from your teachers. Now, guys, we are not yet sure what our school-wide stance on this is going to be. I have a meeting at 11:30 when we're going to figure this out. But Miss Call and I have already decided how we are going to handle this. Now here's the deal, and this is being recorded. Guys, there is the possibility that our choice is going to be in violation of the school-wide approach to handling this. But guys, we are going to make the choice that is best for us. So here's what we're going to do. Guys, when you're in school, it will be as if nothing changed. If you're in school, it's as if nothing changed. It's lecture, it's homework, it's lab, it's whatever we were doing. If you are at home, we do not expect you to stay caught up with what's happening at school. You will not be you won't be watching screencasts, you will not be doing Zoom calls, you will not be learning new material from home. So guys, I don't know a better way to explain this to you than other to say, if you're at home, you have no obligations to this class. Does that make sense? Guys, it's only 2 weeks. Yes, it is going to slow us down a little bit, but I'll be honest with you, in this class, the damage that would be done by having 50% of you learn from home while 50% of you are in school, functionally what's going to happen, guys, is we're just going to create a divide. And everybody in school is going to get it, and everybody at home isn't. And then those groups are going to flop every 2 days. And we've just decided we're not going to mess with that. So if you are at home, you have no obligations to this class. That may not be true in your other classes. But guys, understand in this class you'll have no obligations. So, guys, questions about any of this, I will answer them if I can. But go ahead. Yeah, Maria. Correct. Yep, so Monday is an A day, A through K. Tuesday will be a B day, A through K. And so if you're L through Z, you will not be on campus Monday or Tuesday of next week. Wednesday and Thursday. W. So you won't have school Friday. You won't have school Monday, Tuesday as a W. Your next days of school will be Wednesday, A day, Thursday, B day. Whether or not you have obligations on Monday and Tuesday are up to your teachers. In this class, you do not. Okay? What else, Yellowstone, Regan? Okay. Guys, yeah, please. Yes. Yeah, so functionally what this means is I've got 4 sections of general chemistry, so now I have to teach the same stuff 8 times. How much fun does that sound like? Yeah, I know, right? But it's better than having to go back and reteach half the students because they didn't learn it from home, right? Just a second, go ahead. No, and that's different. Timpanogos went A day, B day, A day, B day off. We're going, so A day, this is Monday, this is Friday, A day, B day, A day, B day, A day, B day, Monday. So we are not taking any more days off other than Friday, this Friday, to get our ducks in a row. Yeah?
So what's next Friday going to be? Is it going to be
It will be an A through K A day. Okay? And guys, understand, let me see if I can find this. I need to be careful about what I show you. So I'm just going to show you. So guys, this is what this looks like. Wednesday, normal school. Thursday, normal school. Friday, no students for prep and cleaning. And then that's the schedule. A day, B day, A through K. Wednesday, Thursday, A day, B day, L through Z. Friday, Monday, A day, B day, A through K. Does that make sense? Go ahead. You were going to say something. Mm-hmm. That's a good question, and I can answer that. When they count up our total number of cases, it is active cases. And so the minute you test positive, you're excused for 10 days, right? So when we count our COVID numbers, it's the number of current active cases that we have. So I'm starting to get students back that were COVID positive. They don't count towards our totals. Is that okay? Did that answer your question? Go ahead. Yes. It's interesting. Well, I should be careful. There have been requests from teachers that if we're going to do this, could we please extend back to our normal schedule? There are some problems with that, one of which is lunch. It would put lunch back in the middle of the day, first, second, third, lunch, fourth, which could be problematic relative to social distancing. So we're seeking input on that. Right now, it looks like we'll stay on our current schedule. Could change. So, yeah. And Sam, I saw you taking a picture of this. You'll get an email with all of this in it as well. Somebody else was going to say something, I think. No? Guys, what else? Again, I'm being as transparent with you as I can. There's a lot we don't know. Go ahead. Yeah, right. Can we talk about that for a minute? Thank you. I appreciate the feedback. But guys, you're going to find with varying degrees of success, your teachers are going to be communicating with you what this is going to look like. If you ever find yourself going, I don't know what I'm supposed to be doing, the answer to that is send an email. But guys, we need to talk about this. This is me being an adult in your life. And guys, I get it. Email for you is like Facebook. it's like 15 generations ago, and nothing good happens on email, just like Facebook is dated and now everything's on other platforms. Guys, I understand that. But you have to understand that the adult world still functions on email. Email is where business gets done. And that business can be the business of school. So if you need to reach out to your teachers, do it via email. But understand, you are not texting your teachers. So guys, let's talk about this. Many times I will get emails from my students that are basically, hey, yo, what's up? What did I miss? Delete. Guys, when you send an email, the first thing that you need to do is put something in the subject line. I get so many emails every day that if I don't see a subject, I delete it. So the subject needs to be your name and perhaps what it is that you need, right? Sam Ford, hey, could you help me? I'm not sure what to do, or whatever that looks like. But guys, it's got to be your name, and then as you're typing, there's a salutation. Mr. Knappenberger, comma. Because you're writing a letter. You're not writing a text. You're not DMing me, right? So, and then guys, it's complete sentences, it's punctuation. Some of you are like, what are those? But guys, seriously, you want to be thinking clearly, you want to think through what you're going to write. Guys, formalize this, but please don't hesitate to reach out to your teachers. If you really get stuck and you're like, I just can't get this teacher to respond, email me and I'll go track them down. Seriously, I'll do that for you. Let me know. I'd be more than happy to get involved if I can. So guys, what else do we need to talk about? Are we okay? Are we good? Okay. So guys, we have chewed through the first half hour of class, but we've got some really interesting stuff that we're going to do today, which involves a gorilla in an apron. Oh, just you wait. All right. I know, right? So guys, what I need you to do is grab the note-taking sheet that you have in front of you. And we are going to dig in and get going. So I need to get rid of this, and I need to get rid of this, and I need to grab a hold of this. And guys, here we go. We are now shifting gears and we are digging into new material. We are not going to rush, but we're also not going to drag our feet, because we need to get this information in your hands, especially given the fact that for some of you, I will not see you again until next Wednesday. I know, right? Weird. Okay. So guys, with that said, today, and gang, I know you all well enough to know that you're going to love this. Guys, today we are actually going to talk about subatomic particles and atomic structure. And guys, we are going to answer 3 really interesting questions. Where do atoms come from? How big are they? And what are they made of? Now guys, along the way, we're going to watch some videos. Along the way, we're going to play with some ideas. But guys, as we dig into this, the question might become, how does this conversation fit into what we're talking about? And guys, the answer is, it's the whole bottom left corner of this triangle. Guys, when we talk about atoms, we're talking about elements. And when we talk about elements, we are talking about the fundamental building blocks of everything that's around us. Now, guys, with that said, allow me, if you would, for just a minute to share a thought. Guys, we are going to talk about some things today that have the potential to be divisive. If you don't understand this, there is tension that exists in our world between faith and science. If you don't understand what I'm talking about, think about creation and evolution. Was it 6 days in a garden, or was it billions of years over time? But guys, here's the thing that's interesting. If you don't feel the tension between faith and science, all you need to do is look out over Utah County. And guys, there are all sorts of people right now that are saying science tells us this about COVID and da-da-da-da-da-da-da-da. And then there's a whole lot of people that say, no, this is a faith issue. That if you just have faith, you won't get sick and da-da-da-da-da-da-da-da. And all of a sudden we got some people wearing masks like they're glued to their face, and some people never wearing masks because it's a violation of their freedom and a lack of faith. And it all crashes together at city council meetings in Provo. Guys, I would suggest to you this. And guys, I'm not going to get into this because I can't. But guys, you know me well enough to know that the most important thing about me is my relationship with God. I have a deeply held faith, but I'm also a scientist. And guys, those things are not in tension. You can believe, you can be a person of faith, and you can be a person of science. And I would propose to you that the deeper you dig into those things, the more tightly they mesh. So guys, please do not think that as we talk about stellar evolution, this is Knappenberger going, there is no God, right? But you can also go, wait a minute, maybe there was evolution without God. But guys, these things can complement each other as well. And I'm not asking you to make that choice. So, guys, with that said, here's what we're up to today. First thing we're going to do is we are going to talk about atomic evolution. You'll notice you have these questions in front of you. And we are now going to answer question number 1, which is, where did all of this stuff come from? Guys, you understand this. We are made of atoms. It's everything. Atoms are reality. The question is, where did they come from? The answer that I'm going to provide you is what we know from science. So guys, follow along. Ready? This wall, this cabinet right here, represents about 11 billion years ago. Guys, this wall over here represents 2020, which is quickly becoming my least favorite year ever. But, so, 2020 over there. And then guys, 11 billion years ago over here. So why 11 billion years ago? And guys, the answer is because we think that our universe is about 11 billion years old. So what was there before 11 billion years ago? I would suggest that perhaps is a question better answered in faith. But, guys, 11 billion years ago, an amazing thing happened. There was this little itty-bitty thing smaller than my pinky that contained the entire universe. And what did it do? It blew up. And when it did, it went bang, and it was a really big bang. And guys, 11 billion years ago, this very little thing that we called the singularity exploded. And as it exploded, it expanded. And as it expanded, and this is where this video is about to start, as it expanded, it cooled down. And eventually it got cool enough that protons and neutrons and electrons could form out of the stuff that blew up. And once it finally got cold enough that protons and neutrons and electrons could form, those things started sticking together. And the positive protons and the negative electrons attracted each other, and they formed hydrogen atoms. But guys, hydrogen is matter, and matter has gravity, and these atoms started to cluster together, and maybe they looked something like this. So guys, this is where we are going to pick up. This is probably 8 or 9 billion years ago. Big Bang was 11 billion years ago, we think. But guys, we are going to pick up the story at the point where our universe was just huge clouds of hydrogen. And these hydrogen atoms all started to come together because of gravity. And as they did, more and more of these atoms piled together. And eventually, let me make sure I've got the sound right. I didn't. And eventually, guys, this is what we ended up with. Huge clouds of hydrogen clustering together. Here we go.
As hydrogen piles on, the central region grows more and more dense, until something brand new lights up the universe. A star.
So guys, as these hydrogen atoms pile together, eventually we get enough of them that they become heavy enough that they cluster together and they turn into what we call stars. Did you guys know that? That stars are just huge balls of hydrogen? Let's keep going.
These first stars are hydrogen giants, 100 times or more larger than our own sun. Such massive stars are short-lived, 2 or 3 million years at the most, and they go out with a bang. In explosions so big, they've been dubbed hypernovae. And it's with these cataclysms that the universe begins to accumulate the building blocks of life. All the atoms in the universe heavier than hydrogen and helium are forged by stars.
Stars are really interesting. They don't just sit there. They don't because they last so much longer than we do. We think they're permanent.
Stars are the ultimate alchemists. They turn light elements into heavier ones. They get the energy that they need to glow that way. The star begins its life made out of hydrogen and helium mostly, about 70% hydrogen, 28% helium in the case of the sun.
In a star's core, the temperature and pressure are so high that hydrogen atoms fuse together to make helium. Hydrogen fusion releases prodigious amounts of energy.
That's a good word, prodigious. I think you guys should try to work that in sometime today. It just means a lot.
Heat and light of a star.
That's the story for 90% of the life of a star, fusing hydrogen to make helium.
Eventually, though, the star runs out of hydrogen and begins to fuse its stocks of helium, making yet heavier elements.
And so the way it works, and it always works this way, is that it contracts and it gets hotter. And if it can find something new to burn, whether it's the kitchen sink or coal or whatever, it'll burn it.
Helium is taken 3 at a time to make carbon.
You can add one more helium to that carbon and make element number 8, oxygen.
That's a tremendous step forward. You get carbon and nitrogen and oxygen made in stars.
Now this is great because on the board we already have the principal elements of life.
Organic chemistry is the chemistry of carbon.
Carbon fuses next, and still heavier elements begin to form.
Sulfur, argon, chlorine.
Potassium, calcium, scandium. The pace of this gets faster and faster.
Back in the middle, silicon is starting to burn at 3.5 billion degrees, stupendous temperature.
It makes titanium, vanadium, chromium,
Manganese, cobalt, nickel, and iron.
Iron is really the end of the road. It's sort of the nuclear turnip out of which you just cannot squeeze anymore.
It's the end of the game. A star that has relied on fusion has come to the point where it has nothing more to spin.
The star is suddenly caught in a disaster. There's radiation going out from the outside, but deep in the inside, there's no more fuel.
Iron can't fuel this stellar furnace, and so, when a star builds up too much iron, it dies.
The core collapses, it bounces,
And it begins to move out, first slowly and then faster and faster.
and that sends a very sharp wave back out through the star.
And now what was falling down is going out, the whole thing's blowing up. And you've made a supernova.
A supernova explosion can be as bright as 4 billion stars like the sun.
A stupendous explosion.
Such outrageous energies overcome the iron barrier, cooking atoms into all the rest of the elements on the periodic table.
So starting down here, you can go copper,
Zinc,
gallium,
germanium,
arsenic,
zirconium, niobium, molybdenum, technetium,
strontium,
rhodium,
lutetium,
antimony,
ytterbium,
tellurium,
thorium,
iodine,
radon,
xenon, cesium,
francium,
barium, lanthanum,
tellurium,
cerium,
indium,
actinium,
xenon,
thorium, protactinium,
cesium.
uranium. Done. That's enough elements.
We are all stardust. The carbon in our bodies, the iron in our blood, the calcium in our bones. Every last atom was formed in a star.
All right, guys, let's take a shot at these questions. So let's review for a second to make sure that you understand the timeline. So guys, do this with me. Before we write down the answers, let's talk. So guys, 11 billion years ago, what happened? Big Bang. That exploded and it expanded, and as it cooled, what was the first element to form? Hydrogen. Those hydrogen atoms clustered together, and what did they turn into? Stars. Inside those stars, hydrogen atoms start to fuse together. And guys, if you take two hydrogen atoms and fuse them together, what do you get? Helium. So slowly over time, stars like our sun, you guys know this, right? The sun is a star. Guys, the sun and other stars are taking hydrogen and making helium. Eventually they start to run out of hydrogen. So what do? They start fusing helium atoms together. And then we start getting these heavier and heavier and heavier elements. But when does that stop working? What element is the end of the road for stellar creation of elements? Iron. Guys, iron is the end of the road. So as these stars put these elements together, when these elements get heavy enough that they are iron, iron is no longer fusible in a star. Therefore, the star runs out of fuel. So what happens to that star when it runs out of fuel? It blows up. And what do we call the explosion? A supernova. And when that star blows up, now all of a sudden there's enough energy available even to fuse iron with other atoms, and that explains all of the elements up to uranium. That's the end of the road. So let's pull this together. Guys, where did all the hydrogen in the universe come from? The Big Bang. Number two, simply put, what are stars? So stars are big balls of what? Hydrogen turning into heavier elements. But guys, the important term here is fusing. These elements are fusing together to make heavier elements. Then gang, question number 3. What is the heaviest element that stars can produce? Iron. Element 26? Yep, element 26, which is iron. So where then, guys, do the heavier elements come from? When the star blows up, what do we call it? Supernova. And that's where the heavier elements come from. Then, guys, finally, what is the heaviest naturally occurring element? How far can supernova get us? Uranium. So, guys, if you're ever interested in the deeper evidences for these things that I'm sharing with you, I would love to share more. But for now, guys, you just need to know that the working scientific explanation for where these elements came from are Big Bang, stars, and supernova. You get the idea? Okay, so guys, we have now answered question number 1. Remember, we had 3 questions. Question 1 is, where do the elements come from? Question number 2 is, how small are these things? So guys, that's the next thing we're going to talk about. How small are atoms? Guys, you're going to hear some things in this video that are somewhat troubling. And you're going to see a gorilla in an apron, but that's a whole other story. But, guys, we are going to stop this video periodically to every now and then to talk about what on earth is this guy talking about. So, the video that we're going to use to talk about the question, how small are atoms? Some of you may know where this came from just by the music. Sound familiar? It's a TED Talk. Guys, TED is actually the Symposium of Technology, Engineering, and Design, I think. Anyway, they basically get smart people together and go, hey, talk about interesting things. So they approached a physicist at a California university and said, hey, would you be willing to put something together about just how ridiculously amazing these things called atoms are that make up everything around us? This is what he came up with.
You probably already know that everything is made up of little tiny things called atoms. You might even know that each atom is made up of even smaller particles called protons, neutrons, and electrons.
You guys knew that, right?
And you've probably heard that atoms are small. But I'll bet you haven't ever thought about how small atoms really are. Well, the answer is that they are...
Why the mouse? No idea.
Really, really, really small. So you ask, just how small are atoms? Well, to understand this, let's ask this question.
Okay, so now guys, you got to really tune in. How small are atoms? Here's the analogy.
How many atoms are in a grapefruit? Well, let's assume that the grapefruit is made up of only nitrogen atoms, which isn't at all true, but there are nitrogen atoms in a grapefruit. Well, to help you visualize this, let's blow up each of the atoms to the size of a blueberry.
Okay, so the question that we're answering is, how big is an atom? The question back was, how many atoms are in a grapefruit? So now what he's doing is he's cutting into the grapefruit and he is inflating each one of the atoms until it's the size of a blueberry, like the size of the tip. You know what a blueberry looks like. So guys, here's the question. If you take all the atoms in a grapefruit, inflate them to the size of a blueberry, how big does the grapefruit become?
And then how big would the grapefruit have to be? It would have to be the same size of, well, actually, the Earth.
Got it? So guys, if you take all of the atoms in a grapefruit and blow them up to the size of a blueberry, the grapefruit becomes the size of our planet.
That's crazy. You mean to say that if I filled the Earth with blueberries, I would have the same number of nitrogen atoms as a grapefruit?
Can you picture that? You can't. But guys, imagine looking down, digging a hole into the Earth, and you're like, oh my gosh, the Earth is actually full of blueberries. Oh yeah, make a heck of a pie. But guys, the Earth full of blueberries, that's how many atoms are in a grapefruit. Let's keep going.
That's right. So how big's the atom? Well, that's really, 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 really small.
That disturbs me.
And you know what? It gets even more crazy. Let's now look inside of each atom.
Okay, so now we're going to dig inside of the atom and start talking about the nucleus, the middle of the atom.
That's the blueberry, right? What do you see there? In the center of the atom is something called the nucleus, which contains protons and neutrons. And on the outside, you'd see electrons. So how big is the nucleus? Well, if atoms are like blueberries in the Earth, how big would the nucleus be? You might remember the old pictures of the atom from your science class where you saw this tiny dot on the page with an arrow pointing to the nucleus. Well, those pictures, well, they're not drawn to scale, so they're kind of wrong. So how big is the nucleus? So if you popped open the blueberry and were searching for the nucleus, you know what? It would be invisible. It's too small to see. Okay, let's blow up the atom, the blueberry, to the size of a house.
Okay, so now our atom is the size of a house. If the atom is the size of a house, how big is the nucleus?
So imagine a ball that is as tall as a two-story house. Let's look for the nucleus in the center of the atom. And you know what? It would just barely be visible. So
guys, now the question is this. If we blow up an atom to the size of a house and the nucleus is still mostly invisible because it's still too small, how big does the atom have to be in order for the nucleus to be visible? Ready for the answer?
get our minds wrapped around how big the nucleus is, we need to blow up the blueberry up to the size of a football stadium.
Lavelle Edwards Stadium. So guys, if you blow up an atom to the size of Lavelle Edwards Stadium, now the nucleus by scale becomes visible.
So imagine a ball the size of a football stadium, and right smack dab in the center of the atom, you would find the nucleus. And you could see it. And it would be the size of a small marble.
Got it? So guys, if you take an atom and blow it up to the size of a Lavelle Edwards Stadium, then the nucleus would be like a marble sitting on the 50-yard line. Now here's the question. What else is inside the atom? If the nucleus is on the 50-yard line, what else is inside the atom? Well, electrons, right? I like what you did, Kevin. We got things moving around, right? What are those things that are moving around? Electrons. And where are they? They're at the very top of the bleachers, guys. If you take an atom and blow it up to the size of a football stadium, the nucleus is the size of a marble, and the electrons are up in the cheap seats. What else is inside of an atom? Nothing. Guys, atoms are 99.99% empty space. So why are we solid if the atoms that make us up are 99.99% empty space? Because the electrons are moving. We'll talk more later.
And there's more. If I haven't blown your mind by now, let's consider the atom some more. It contains protons, neutrons, and electrons. The protons and neutrons live inside of the nucleus and contain almost all of the mass of the atom. Way on the edge are the electrons. So if an atom is like a ball the size of a football stadium with the nucleus in the center and the electrons on the edge, what is in between the nucleus and the electrons?
So he's asking, what's in the stadium, right?
Surprisingly, the answer is empty space. That's right, empty. Between the nucleus and the electrons, there are vast regions of empty space. Now, technically, there are some electromagnetic fields, but in terms of stuff, matter, it is empty. Remember, this vast region of empty space is inside the blueberry, which is inside the earth, which really are the atoms in the grapefruit.
Okay, now don't turn away. Here it comes.
Okay, one more thing.
I warned you. I did warn you. Okay, one more to go. Ready? So here's what we know. Atoms are ridiculously small. Think blueberries inside the earth. But then inside the atom, the nucleus is ridiculously small, and they're mostly empty space. But guys, here's the other thing you need to know, and maybe you caught this. Where is all of the mass in an atom? It's in the nucleus. So guys, we learned about density, right? Mass divided by volume. So all the mass of an atom is in the nucleus, but the nucleus is very small. So we've got mass in a very small space, which means it's very dense. So the last thing we're going to talk about is how dense is the nucleus.
Can even get more bizarre. Since virtually all the mass of an atom is in the nucleus, and now there is some amount of mass in the electrons, but most of it is in the nucleus, how dense is the nucleus? Well, the answer is crazy. The density of a typical nucleus is 4 times 10 to the 17th kilogram per meter cubed.
You guys got that?
But that's hard to visualize.
You want to write that down?
I'll put it in English units.
Don't.
2.5 times 10 to the 16th pounds per cubic feet.
Okay, you got that? Yeah, me neither. So guys, how dense is the nucleus? Ready?
Okay, that's still kind of hard to figure. Okay, here's what I want you to do. Make a box that is 1 foot by 1 foot by 1 foot.
So I did. This is it. This is my box that is 1 foot by 1 foot by 1 foot.
And let's go and grab all of the nuclei from a typical car. Now, cars on average weigh 2 tons. How many cars' nuclei would you have to put into the box to have your 1 foot box have the same density of a nucleus?
Get it? So guys, the question is this. We understand that the matter inside of the nucleus is very dense because the nucleus is very small. How dense is it? So the question is, what would we have to put inside this box to make the matter inside this box as dense as the nucleus of an atom? Ready for the answer?
Is it 1 car? 2? How about 100? Nope, nope, and nope. The answer is much bigger. It is 6.2 billion. That is almost equal to the number of people in the earth.
Got it? So guys, if you want to make the matter inside this box as dense as the nucleus of an atom, you have to jam 6.2 billion cars into this box. And when you have crushed 6.2 billion cars into this box, the matter inside that box is now as dense as the So guys, what do we now know? We now know that atoms are really small. How small? Think blueberries inside the earth. We now know that the nucleus is very small. Think marble inside of an empty football stadium. And now we know the matter inside that nucleus is very dense. Think 6.2 billion cars inside of this box. So guys, atoms are crazy on a scale that we have absolutely no real way of understanding. So guys, if that's the case, the question then becomes, how do we talk about atoms? And the answer is, we can actually make measurements and understand some things about atoms. So guys, we're now going to answer the last question. You've got the notes in front of you. Let's fill this out. So where did atoms come from was question 1. We talked about it. Question number 2 is, how small are these things? We talked about it. Question number 3 is, what are they made of? And guys, this is going to be the collection of information that you need to know about what they're made of. Do this with me. So guys, you know that atoms are made of protons, neutrons, and electrons. Now guys, let's do this. Where are the protons and neutrons in an atom? In the nucleus. Therefore, we call these nucleons. And then the electrons are zooming around the outside. Now guys, these are the things that you need to know about these particles, and then we're going to make this practical. So guys, it goes like this, moving left to right. When we abbreviate proton, we abbreviate that capital P positive. The capital letter means that it is massive, and the positive is the positive charge. So guys, please do not write down the next number. So, how massive is a proton? Well, guys, the answer is this. Don't even write it down. It's 1.67 times 10 to the negative 24th grams. Written out, it looks like this. Guys, that is the mass of a proton. But when you're as small as the nucleus, that's like a dump truck. But guys, here's the problem. This number is so cumbersome to work with that we actually use a different unit of mass called the atomic mass unit. And in atomic mass units, the mass of a proton is 1. Now, what is the charge of a proton? Well, it's given by the sign. It's positive. But guys, it's not just positive. It's positive 1. So guys, if you understand what we just talked about, I'll bet you can fill out the next part of this chart by me simply showing you the abbreviation for a neutron. Guys, neutrons are capital N0. What does the capital letter tell you about the mass of a neutron? Is it massive? Oh yeah. It's actually exactly the same mass as a proton. Again, you don't need to know the number in grams. But guys, what is the charge of a neutron? Well, that's the superscript. What does the little 0 tell you? No charge. Neutrons do not have a charge. Now guys, what about this? The abbreviation for an electron is this. Why is it lowercase? It's not very massive. And then the negative tells us the charge. So guys, please don't write this down. But this is the mass of an electron. It's about 2,000 times less massive than a proton or neutron. It does have mass, but it's very, very small. As a matter of fact, it's so small, we call it 0. Electrons do have mass, just not very much. But then, guys, what is the charge of an electron? Not just negative. Good, it's -1. And guys, why is that important? Because the charge of protons and the charge of electrons cancel each other out. We'll talk in a minute. Okay, so guys, here's where we are. What do protons and neutrons have in common besides they're in the nucleus? Well, guys, the answer is they have mass. Protons and neutrons are our mass-carrying particles. Now guys, what about this? What do protons and electrons have in common? They carry charge. There is almost a poetic beauty to this. Protons carry mass and charge. Neutrons carry only mass. Electrons carry only charge. Now guys, there's one other thing that you need to understand, and then we're like a step away from you getting some homework done. Guys, the last thing you need to know about these atoms before we move forward is that atoms don't have a charge. I would write this down below. Oh, it's already there. Atoms don't have a charge. Here's the question. If atoms don't have a charge, what does that tell you about the number of protons and the number of electrons in an atom if they don't have a charge? They got to be the same. The number of protons equals the number of electrons because they cancel each other out. All right. So now, guys, grab your periodic tables. We've got one more thing to talk about, and we're done for the day. So understand the question that we're asking. What are atoms made of? And we know it's protons, neutrons, and electrons. The question is, how many? Well, guys, this information is on our periodic table. So do this with me. Guys, on our periodic table in the upper left-hand corner, we've got the atomic number. 1, 2, 3, 4, 5, 6. Guys, what does the atomic number, which is abbreviated Z, tell us about atoms? You should already know this. How many what? Protons. You could just write down protons. So guys, the atomic number tells us the number of protons. See where you have this in your notes? Then guys, there's another number. This little number that's up here in red, that little number up here in red, which is called the atomic mass, tells us the number of protons and neutrons. Guys, the units for atomic mass are atomic mass units. So this tells us the number of protons and neutrons. Now guys, you'll notice that the numbers on your periodic table are not whole numbers many times. We're going to round, and we'll talk more about it when I see you next. But guys, when we have this information, atomic mass and atomic number, it can be represented in one of two ways. One of the ways that we do this, like with carbon, is we write the abbreviation of the element, and then we put the atomic mass on top and the atomic number on the bottom. Carbon is element 6 with a mass of 12. We can also do it like this. We can just call it carbon-12. It's not a negative sign. It's carbon 12. We don't need to put the 6 because we know that carbon is element 6. All right, guys, we're one step away. We now have all the information that we need to figure out the number of protons, neutrons, and electrons in an atom. So guys, let's talk about it. You ready? Can I go to the next slide? Here we go. So guys, how many protons are in an atom? How do we know? What tells us how many protons are in an atom? The atomic number Z. Now guys, how many electrons are in an atom? The same. Because the positives and negatives need to balance. Now guys, this is a tricky question, but I know you guys will figure it out. How can we figure out how many neutrons are in an atom? Good. The atomic mass tells us protons and neutrons. The atomic number tells us protons. All we have to do is subtract, and that tells us the number of neutrons. You okay? So guys, with that said, let's apply this by drawing a picture. You've already got it. So guys, we are going to take this picture and we are going to allow this to represent a potassium atom. Now guys, here's what we're going to do. Join me at the board. This inner circle represents the nucleus and this outer circle represents the electrons. Is this drawn to scale? No, because if this circle was the size of a marble, how big would this circle be? Lavelle Edwards Stadium. You starting to get it? But guys, we obviously can't do that, so we're going to fudge a little bit. This is the nucleus, those are the electrons. So guys, here we go. Potassium is element number K, is letter K. It's element number 19. So guys, how many protons are in the middle of a potassium atom? 19. It's the atomic number. If it's not 19, it's not potassium. But now guys, what about this? If there's 19 protons, there are also 19 electrons. But guys, if there are 19 protons, there are not necessarily 19 neutrons. So how do we figure out how many? Well, potassium is element 30, its mass is 39.0983. We round that to 39. 39 minus 19 is 20, and there's 20 neutrons in the middle. You get the idea? Okay. So guys, this is what you're doing in homework today, but we're not going to do it in circles. Guys, grab your homework. We're going to do the first couple together. So guys, what I've got on the screen should be what you have on paper. And let's do the first two together, and then you'll have a little bit of time to work on this, very little, but a little. So guys, here we go. Helium is He with an atomic number of 2 and a mass of 4. So guys, how many protons are in a helium atom? 2. Because these columns are always the same. The atomic number tells us the number of protons. Now guys, let's do the easy fruit. If there's 2 protons, how many electrons are there? Also 2, because these columns are always the same. So now guys, we need to do neutrons. And it does happen to be 2. But the reason that it's 2 is this is A minus Z. 4 minus 2 is 2. You good? Let's do the next one. Oh gosh, they didn't give us, we're going to skip this. They didn't give us any information. But guys, they told us the atomic number. It's element 12. So what is element 12? Magnesium. So we come over here and we go magnesium. Guys, it's abbreviated Mg. Big M, little g, do it right. Now guys, we know that magnesium is element number 12. Now we need its mass. And its mass is 24.3, which we round to 24. Now guys, what's the atomic number? 12. So that tells us 12 protons. Also 12 electrons. They already told us it had 12 neutrons, but 24 minus 12 is 12, and we're good to go. So, guys, when I see you next, we will turn in this homework assignment. Is it double-sided? Yeah, there is a back to it that goes through all the other stuff that we talked about. Now, guys, again, we have just a couple minutes left. Please, guys, these are the things that you're committing to for the next couple weeks. Hang on a second. Guys, these are the things that you're committing to not just in this class, but in all of your classes. You are going to be a force for positivity in the middle of this. Number 2, you are going to communicate well and often with your teachers. And number 3, guys, you are not going to hesitate to ask for help when you need it. Do you promise? Okay. So, guys, we've got a couple minutes left. We will go when the bell rings. Have a glorious day.